The final assumption that we made of the classical linear regression model was that the disturbances in that model were normally distributed. Why did we need to assume normality? Well, we needed to assume normality in order to make statistical inferences from the sample estimates that we got to the corresponding population parameters. In other words, we needed to assume normality so that t-test statistics follow a t-distribution, f-test statistics follow an f-distribution, and so on. What I want to do now is to look in some detail at this normality assumption and look at situations under which it might be violated, look at what problems that might cause and how we might get around them. Now, there are many tests for non-normality in a set of data, and most of these non-normality tests can either be applied to a set of raw data, that is to actual variables themselves, or they can be applied to the residuals from an estimated model. The most commonly used normality test is known as the Bearish Arc Test, and this is the one that's programmed up in eViews and microfit and so on. The Bearish Arc and most other normality tests use the property of a normally distributed random variable that it is completely characterized by its first two moments. That is, if I know that some series is normally distributed and I know its mean and variance, then I know everything about that normal distribution. We couldn't have two different normal distributions with the same mean and variance because a normal distribution is entirely characterized by what we call the first two moments of the distribution, which are the mean and the variance. What we can do, therefore, is to examine what we might call the higher moments of the distribution of residuals, and looking at the properties of those higher moments will tell us if the residuals are approximately normally distributed or not. So a normal distribution is defined to have a zero skewness and is defined to have a coefficient of ketosis of 3. What are skewness and ketosis? Well, skewness and ketosis are the standardized versions of the third and fourth moments of a distribution. If we have a look at a couple of plots just to see what skewed and non-skewed distributions look like, first of all, probably everybody already knows what a skewed distribution is. A normal distribution is characterized by symmetry about its mean value. And for a standard normal distribution, that mean value will be 0. So a normal distribution is symmetrical about its mean value. A skewed distribution, on the other hand, is not symmetric about its mean value. It's asymmetric. It will have one tail of the distribution being longer than the other one, so it won't be symmetric about its mean. So skewness is the standardized third moment of the distribution. The standardized fourth moment of the distribution is known as its ketosis, and the ketosis of a distribution measures how fat the tails of that distribution are. So, for example, if we look at this plot here shows the distribution of an actual set of data using the black line, and that is plotted against the distribution of some random variable which follows a normal distribution with the same mean and variance. So the black and the blue lines are from different distributions. The black line is from some actual data actually, and the blue line is from a normal distribution with the same mean and variance as the black line. Now if we look at the black line, interestingly the properties of that black line are also the properties that almost all asset return time series, and indeed many other time series, have in economics and finance. So if we think for a minute about actual series rather than residuals, and we'll come back to talking about residuals in a little while, often it's the case that many series in economics and finance show this same systematic departure from normality. And this systematic departure from normality is sometimes known as Lepto Ketosis. So the black line is what is sometimes known as a Leptokurtic distribution. So a Leptokurtic distribution is one that has, first of all, it has fatter tails than a normal distribution. So it has more of the distribution in the extremes than a normal distribution with the same mean and variance. Secondly, a Leptokurtic distribution has a higher peak at the mean. That is, it has more observations close to zero than a normal distribution with the same mean and variance would have. Finally, because these distributions in the plots are all scaled so that the area underneath the curves is always the same, it's always 1, if the Leptokurtic distribution shown by the black line has fatter tails and a taller peak at the mean, it must be smaller somewhere than the normal distribution in the blue line. And the Leptokurtic distribution is smaller in what we call the shoulders of the distribution. So the Leptokurtic distribution has fat tails, a higher peak at the mean, but comes in more narrowly in the shoulders of the distribution. And as I said, interestingly, many time series in economics and finance have this same property as the black line. So we can use this property of normal versus not normally distributed random variables, that is, they might be skewed or they might be leptokurtic, to decide whether a series is normally distributed or not. Now, just before we go on to do that, I want to talk about another possible departure from normality that we could have. A leptokurtic distribution is one where the tails of the distribution are fatter than the normal. We could have the opposite thing happening. That is exactly the opposite deviation from normality than the one described by the black line on this plot. And that exactly opposite distribution would be called a Platykurtic distribution. Now, Platykurtic distributions are very, very rarely found in practice in economics and finance, but in theory they do exist. What would a Platykurtic distribution look like? Well, these things are actually quite hard to draw, and I'm particularly bad at drawing these things. But let's suppose that we had a normal distribution, which is the black line here. So the black line is a normal distribution. What would a Platykurtic distribution look like? Well, it's not very attractive, but it would have thinner tails than the normal, fatter shoulders, and be less peaked at the mean. So it would have a kind of relatively square shape. So it might do something that looked a bit like this. So that would be the Platykurtic distribution. So a Platykurtic distribution in the red line here would be one with thinner tails than the normal, a lower peak at the mean, but bigger shoulders. Now, as I said, this is always hard to draw freehand like this, especially when you're as bad at art as I am, but also these are hard to draw because we never actually see them in practice. So this only exists as a kind of theoretical possibility. Finally, a fat tail distribution is leptokurtic. Thin tail distribution like the red one here is platykurtic. What do we call a normal distribution? Well, a normal distribution is defined as being mesokurtic. So a fat tail distribution is leptokurtic, a thin tail distribution is platykurtic, normal distribution is mesokurtic. So those are the three possibilities we can have in terms of the ketosis or the standardized fourth moment of the data. Now, if we move away now from talking about actual series and back to the residuals, which is what we were actually interested in testing, as I said, we can examine the extent to which a series is normally distributed or not normally distributed, a series of residuals that is, by examining its coefficient of skewness and its coefficient of ketosis. So the coefficient of skewness, defined as B1, is given by the expected value of U cubed divided by sigma squared, which is the variance, obviously, of these disturbances, raised to the 3/2. So we can use a formula like this, substituting the disturbances with their empirical sample counterparts, the residuals, and we can calculate the skewness. You can see now why the skewness is called the third standardized moment of the distribution, because we're taking the cube in the numerator and we're standardizing it by a function of this sigma squared in the denominator. One implication of this is that skewness, and as we'll see in a second, ketosis, are both unit-free. So if we estimate a regression model, okay, and suppose that y is a set of returns, if y has units of returns, then the residuals will also have units of returns. The variance of the residuals will obviously have the units of the square of returns, but skewness and ketosis will be unitless or unit-free whatever the units of the original data were, because we've standardized them in a way that, in a sense, removes the units. So we're taking a cubic term on the top of the expression for B1 and dividing it by something that, in a sense, turns out to be a cubic or third order term at the bottom. Similarly, we could define the ketosis as being the expected value of u to the 4 divided by sigma squared squared. So once again, you can see that we're taking a fourth order term and dividing it by a fourth order term so that units kind of get cancelled out. Now, the coefficient of skewness is defined as B1, the coefficient of ketosis is defined as B2. But a normal distribution has a ketosis value equal to 3. Okay, so a normal distribution will have a value of B1 equal to 0, that is, it won't be skewed, it'll be symmetric, and it will have a value of B2 equal to 3. Now, the value of B2 equal to 3 corresponds to the distribution being mesokurtic. So a normal distribution will have B1 equals 0, that is, it will be symmetric about its mean. It will have a value of B2 equal to 3, that is, it will be mesokurtic. If we have a value of B2 bigger than 3, then that would be the Leptokurtic distribution. So a Leptokurtic distribution would be one where B2 is bigger than, 3, sorry. The Plata-Kurtic distribution would be one where B2 is less than 3. That would be the thin-tailed distribution. Finally, the mesokurtic distribution would be the normal where B2 equals 3. Now, it's easier when we compute the test statistic for determining whether residuals are normally distributed or not. It's usually easier, instead of working with this thing, which is the ketosis, B2, so B2 is the coefficient of ketosis. Instead of working with that, we usually work with B2 minus 3. And B2 minus 3 we could define as being the coefficient of excess ketosis. So B2 minus 3 is the coefficient of excess ketosis. So a normal distribution will have a skewness of 0 and an excess ketosis of 0. So we can test the joint null hypothesis that B1 equals 0 and B2 equals 3 or B2 minus 3 equals 0. And that's what the Bearish Arc statistic does. So we take the skewness coefficient B1, we square it and divide it by 6. We add that to the square of the excess ketosis coefficient divided by 24. We multiply all of that by the number of observations, and that's the Bearish Arc Test statistic. So obviously the more skewed the distribution is, and it doesn't matter which way the skewness runs, it doesn't matter if the distribution of residuals is right skewed or left skewed. Obviously B1 squared will get bigger whichever direction the skewness goes in. And it doesn't matter if the distribution is either thin-tailed or fat-tailed, because once again we're taking B2 minus 3 and squaring it, so we lose the sign anyway. But whatever the departures from these are, the bigger those departures are, that is, the more skewed the distribution is, and the more fat-tailed or thin-tailed the distribution is, that is, the further away it is from being mesokurtic, then the bigger the value of the test statistic will be. So we calculate the value of this test statistic. It follows a chi-squared distribution with 2 degrees of freedom, because obviously we're testing 2 restrictions here under the null hypothesis. So we calculate the value of the test statistic. If it's bigger than the value of the chi-squared 2 from the critical value tables, then we reject the null hypothesis that these residuals are, that the disturbances are normally distributed. If the value of the test statistic is smaller than the chi-square critical value, we don't reject the null hypothesis. And we can say that we don't have much evidence against the null hypothesis that those disturbances are not normally distributed. If we find that the estimated residuals from our regression model seem to indicate evidence of non-normality, what should we do? Well, unfortunately, it's not immediately obvious at all exactly what we should do. So once again, we end up usually using a fairly kind of ad hoc solution. So what could we do? Well, one approach which we could take would be to use a different estimation technique or a different approach to inference which doesn't require the normality assumption. So for example, what we could do is to, instead of obtaining critical values from T and F tables to compare our test statistics with, we could conduct a simulation analysis and construct a new set of critical values for comparing our test statistics with that were appropriate given that our series was not, of residuals were not normally distributed. But that's likely to be tedious in practice, and we know the properties of the ordinary least squares estimator very well, so we don't really want to ditch it. What we can do instead is to use, as I said, a more kind of ad hoc approach that seems to work in practice. Now, it's often the case in practice that the reason that the normality assumption is rejected is that there are one or two very extreme residuals, which we might call extreme outliers, which cause the non-normality assumption to be violated. If we remember the formulae for B1 and B2, that is the coefficients of skewness and ketosis respectively, we know from those formulae that if the residuals are very big, then when we cube them or raise them to the power 4, then obviously they'll become very big indeed. So big residuals caused by observations that didn't very well fit the model will often cause departures from normality in practice. If we were to plot the distribution of residuals, what will often happen when we have big residuals, either big and positive or big and negative, will be that we get a kind of hump in the tails of the return distribution. So a big positive residual would cause a hump in the upper tail of the residual distribution. And that is often in practice what causes the non-normality. So if the non-normality is caused by one or two observations that don't very well fit the pattern of the other data and therefore don't very well fit the model, what can we do about it? Well, there are essentially two approaches that we can use, and both involve removing those observations from the regression model. So the first thing that we could do when faced with an outlier or an observation that doesn't fit the data very well is to physically remove that observation from the data set. So if there was an observation that didn't fit the data very well, that didn't fit the model very well, we take all of the observations for that data point and remove it from the sample altogether. So if you imagine a column of observations on y and columns of observations on all the explanatory variables, it would be as if we removed a row from all of those columns corresponding to that observation. We then re-estimate that regression model, excluding that observation altogether. The second thing that we could do, which would be equivalent to removing that observation, would be to use a dummy variable in the regression model instead. So if, for example, we have a look at this plot, so we've plotted the residuals over time, and we find that the value of that residual plot is bigger in absolute terms for one observation than all the others when we plot it. So suppose, for example, our sample period included an observation for October 1987 when there was a stock market crash. So we can see that the value of the residual during that observation is much bigger in absolute terms than it is for all of the other observations. We could create a new variable which we could call D87M10T, for example, because obviously it's a dummy variable for October 1987, and that new variable would take the value 1 for October 1987, assuming that we were using a monthly series of data, and it would take the value 0 in every other, for every other data point, for every other observation. So if we were to just look at what this observation would, what this new dummy variable would look like, it might appear as follows. So we've got this new variable, D87M10T. And if we were to look at the values it took over time, let's suppose that we had an observation for 1987 M8, 1987 M9, that is September, 1987 M10, which is October, 1987 M11, 1987 M12, and let's say the last one that I put in this list here is 1988 M1, and so on and so on. So if we've got observations on this dummy variable for each of those data points, the values would be 0 everywhere except for this one observation that we wanted to implicitly remove from the regression model, where this dummy variable would take the value 1. So the dummy variable would take the value 1 for October 87 and 0 everywhere else. So that's the way that the dummy variable would be constructed. How does the dummy variable work? Well, because the dummy variable takes the value 1 for just that one observation, it has an identical impact in the regression model to the situation where we'd remove that observation altogether but not included the dummy variable. So to make life simple, let's suppose that our original regression model that we estimated was a simple bivariate regression model of this form. Okay? The two approaches that we could use, that is remove October 87 observations altogether and re-estimate the model, and re-estimating this regression model including the dummy variable would lead to the same end result. So if we were to use the dummy variable approach, the regression that we would actually estimate would be yt equals beta 1 plus beta 2 x2t plus beta 3 d87m 10t plus ut. Okay, so we'd include this dummy variable as an extra regressor in the regression model. Now, the estimated value of this new parameter here will be exactly equal to the value that the residual on this observation that we're implicitly trying to remove would take if we'd not remove that observation. So beta hat 3 would be exactly equal to u hat for 1987 month 10, okay, in the model where we didn't include the dummy variable and we didn't remove the residual. So I'll say that again. The impact of this dummy variable is to have exactly the same impact on the model as if we'd removed that observation altogether. And the way that this works is that the estimated value of the parameter on that dummy variable will be exactly equal to the value that the residual for the observation where the dummy variable equals 1 would have taken if we'd not included the dummy variable and if we'd not removed that observation from the regression model. So for this model in here, the estimated residual from this model would be exactly equal to 0 for that observation. So for this model including the dummy variable, u hat for 1987 month 10 would be exactly equal to 0. Okay, and it would the value of the parameter estimate would be equal to the value of the residual that it would have taken in this original regression model if we had not included the dummy variable and we'd left that observation in. So the implication is that by including the dummy variable in the regression model, we set the residual for that observation to 0. So obviously, if the residual for that observation is exactly equal to 0, when we include the dummy variable in the regression model, then it's exactly the same as if we'd removed that observation altogether. And we can see the impact on the degrees of freedom in the two cases would be exactly the same. So in the first case here, if we remove the observation, okay, then we'd end up with t minus 1 observations and k regressors in the regression model. So we remove the observation, we lose an observation obviously, and we've got k regressors including an intercept. If we use the dummy variables approach, we retain all of the observations t, but we end up with k plus 1 regressors. Okay, so if we remove the observation altogether from the sample, then we end up with t minus 1 minus k degrees of freedom in our regression model. If, on the other hand, we use the dummy variable approach, we end up with t minus k minus 1 degrees of freedom, which is obviously exactly the same. So the two approaches to dealing with one or two extreme outlying residuals are exactly the same. That is, they have exactly the same implication at the end. The residual sum of squares in both cases would be reduced by the same amount because in both cases implicitly the residual for that observation that we're implicitly removing would be 0. So an obvious question to ask is, well, why bother using this dummy variables approach? Why not just get rid of that observation altogether? Well, the answer is that using the dummy variable approach gives us slightly more useful information which we can use than if we remove the observation altogether. If we include the dummy variable, obviously we can get an idea of the value that the residual would have taken for that observation by looking at the estimated value of this coefficient. On the other hand, if we just remove the observation, we wouldn't get any such information at all. The second useful thing about including the dummy variable is that by doing that, we can do a test of statistical significance for this residual. So we can say, is this residual significantly different from 0 or not, by testing the null hypothesis that the true value of beta 3 equals 0. So we could look at the value of this test statistic, and that would tell us the kind of statistical significance of the residual for this particular observation. There are two schools of thought in econometrics about whether we should use dummy variables or some other approach to remove observations or not. The first school of thought says that we shouldn't use dummy variables to remove observations because this is in some senses tantamount to cheating. Obviously, if we use a dummy variable or some other approach to remove observations, we're taking the model, estimating it, finding the parts that the model doesn't explain very well and kind of getting rid of those or sweeping them under the carpet. Obviously, when we use dummy variables to remove observations, the residual sum of squares for that model will fall because we're setting the biggest residuals to 0. Therefore, the R-squared for that model will rise. So in some senses, we're getting an artificial sense that the regression model fits the data better than it actually did by removing these observations. So some econometricians would say that every observation should represent a useful piece of information upon which to estimate the sample parameters, and therefore we should always include all of the observations we've got, and we shouldn't systematically delete the observations just because we don't like them or just because they don't seem to fit our model that we've got relatively well. We should just live with that, and then we should try and explain them rather than removing the problem altogether. The other school of thought says exactly the opposite. The other school of thought says, well, if we've got observations that don't fit in with the pattern of all the others completely, and therefore we could call them outliers, what we should do is, instead of allowing those to kind of upset the properties of our model and influence the parameter estimates in that model, we should remove those observations altogether. Now, it turns out that outlying observations can have a very big impact on a regression model. To see that, consider the following plot. So let's suppose that we've got a set of observations that seem to fit in the bivariate regression context a very similar pattern to one another. So suppose, for example, we drew a bivariate regression model where we had x2t plotted against yt, and let's suppose that we got lots of observations that seem to lie roughly on a straight line, but let's suppose we also have one observation right down here somewhere, which is obviously a long, long way from all of the others. The regression line that best describes most of the data, that is, if we ignore this outlying observation, we'll go through most of the data points and might look something like that. On the other hand, however, if we include this observation in the sample, then estimate the regression model, because by definition ordinary least squares is trying to minimize the residual sum of squares. Okay, the square of the distance from this point up to the estimated line, maybe it's going to be up here somewhere, so the residual sum of squares from that one observation will be relatively large. So because this observation has a very big residual, and when we square it, it obviously becomes even bigger still, ordinary least squares will try extra hard to ensure that there are no observations a long, long way away from the line. So it might quite radically alter the estimated line if we have an outlying observation in our sample. So maybe the estimated regression line, including this observation, might look something like this. Clearly, it's a long way different from the regression line that we would have had if we'd excluded that observation. So the second alternative school of thought says that, in fact, if we think this observation is a genuine outlier, it doesn't fit in with the sample pattern of all the others, we should remove it from the sample, because otherwise it will completely alter the parameter estimates of the estimated model. So we could have an estimated model if we include the outlier where the estimated regression model doesn't very closely fit the majority of the data points. Here we've got a line that's a long way away from most of the data points, just because this one observation is such a long distance from all of the others. Some econometricians would say that's not satisfactory, so we should use a dummy variable or some other approach to remove this observation. Arguably in practice, the practical and pragmatic approach which most econometricians would use would be to say that we should include dummy variables, but we should only use them when we've both got a statistical reason for doing so. That is when we have a very large outlying observation or a very big positive or negative residual that's dramatically changing the values of the parameters. But also we should only do it when we have a theoretical reason for including that dummy variable. So in other words, we need to be able to identify some event from economic or financial history that would mean that this observation had very different characteristics from all of the others, and therefore probably wasn't very representative of the data as a whole. So a stock market crash, or an observation caused by a terrorist attack or a strike or a freak weather event might be examples of exactly this kind of thing, where we got a genuine reason for thinking that this observation didn't fit in with the pattern of all the others, and therefore it could quite comfortably be deleted. If we go back through time to our kind of the history of what our series represents, and we can't find a sensible reason why this observation doesn't fit in with the pattern of all the others, then some people would argue that we should still leave that observation in. That is, we shouldn't delete it. So the jury is still out in some senses on whether dummy variables are a good idea or not, but in practice many econometricians make use of them in this way.